Welcome back, everyone. So, in the last lecture, I explained linear combination of vectors, span of vectors, linear dependence, independence, and basis for vector space. So, if you haven't watched those videos, then I highly recommend watching them as they are the building blocks of linear algebra and also very important to understand the linear transformation topic. Okay, so today we will understand what is linear transformation. Okay, so before understanding what is linear transformation, we need to see what is transformation in itself. What is transformation? All right. So transformation is the word originated from transform, and the meaning of transform is basically change. If there is some change, then we say it got transformed, and that is what transformation is. Okay, so this topic transformation, linear transformation, has basically two aspects. It has two aspects to it. The first one is the theory part, the maths part, in which I will be explaining you what is transformation, what is linear transformation, how it is different from other type of transformation and all. Okay, the second is the visual aspect, the visual part. So basically we need to understand that what transformation do uh, to a given space. If we have a 2D input space and we apply a transformation, especially a linear transformation, so what is happening behind the scene, that is very important to understand. Okay, so the word transformation is originated from transform, which basically means change. So anything which result in change is transformation. So for example, let us suppose we have a black box, we have something, this black box do something, we provide some input to it and it gives us an output. Then this is also a transformation. This box here is doing transformation. And if you see, given an input, we transform it to get an output. This is very similar to functions, right? This is also this is what functions do. And in fact, in linear algebra, functions are nothing but transformation. Okay, when I say functions in linear algebra, it is transformation. All right, and transformation could be of many type, like given a space, you can wrap it, you can shift it, you can do anything. All right, but the main transformation which is important and which is the heart of linear algebra is the linear transformation. Rest of the transformation are not studied in linear algebra. Only this special type of transformation, which is linear transformation, is studied. Okay, so first of all, uh, what is linear transformation? So for throughout this lecture I will be denoting this linear transformation with the letter T. Okay, so for example, you have this transformation T and it take a vector V. All right, this vector V is from the input vector space. From the input vector space, let us suppose for now this is the 2D xy plane, this is the 2D xy plane, and we have this vector V. All right, and this linear transformation LT transform this vector V and we get another vector, let us suppose W. This is the transformed vector W, which is nothing but transformed TV. All right, and this is our output vector space. And for now, let us suppose this output vector space is also 2D, so we are transforming a vector from 2D to 2D. So let us suppose we get this one, and this is nothing but the transformed V. All right, so for now just think T as some black box which is transforming vector from input vector space to output vector space, and I will explain this black box in detail later on. But for now, let us suppose that this T do something with the input vectors and transform it into the output vectors. All right, so now come the next thing. So this transformation T assigns an output vector TV to each input vector V, right? So this is not just true for this v, any vector v belonging to R2, because this R input space is xy plane R2. Okay, any vector v belonging to R2 has an image TV, transformed v, which also belong to R2, because this is a mapping from R2 to R2, right? So here this mapping is from R2 to R2, xy plane to xy plane, right? So for this transformation to be linear, it should meet two conditions. The first and foremost condition, condition A, yes, the first condition is the transformation of two vectors v and w, the sum of the transformation of sum of two vectors v and w should be sum of their transformed vectors. All right, and this should be true for all vectors v and w belonging to the input vector space, which is R2 in this case. And the second condition is transformation of c times v, that is the scaled version of vector v, is nothing but c times transformation of vector v. Okay, so this condition remains same, and here c is c is a real number for all c belonging to the real number. Okay, so these are the two conditions for linear transformation. Now we will understand it in detail. So the first condition, what it is saying, so the first condition is saying, for example, we have two vectors in the input vector space. This is the first one v, and let us suppose this is the second one w, right? And we get another vector, let us suppose we get another vector z, which is the addition of these two vectors v and w, right? Maybe we get, if I place here, then I think somewhere here I will get this thing v plus w. So it is saying that the transformation, like if I transform this added vector v plus w, that is this one, is same if I first transform the vector v. So let us suppose I first simply transform the vector v. So let us suppose this is somewhere here, and I transform the vector w. Let us suppose this is somewhere here. So doing transformation on these added vectors is same as if I transform them individually, that is tv and tw, and then edit them. You got it? So either you can first add the vectors and then apply the transformation, or you can first apply the transformation individually and then add the transformed vector. So the first property says this of linearity. Second is also very similar. Second is saying that, for example, if we have only one vector v and we scale it by c, and this become c times v, then the transformation of c times v is same as if I first transform v and then multiply by c. So for example, if I first transformed v, so this is tv, and then I scaled it, and this becomes c times tv. Okay, so these are the two conditions. Now if you see what transformation is doing, it's just doing two things. Linear transformation is doing two things visually. The first thing it is doing is it is either stretching or squashing or maybe flipping the vector, basically scaling the vector, and or it is doing some rotation, or a combination of both. So either after transformation, if this is the vector, after transformation this transformed vector will be stretched, it will be scaled, basically it will be scaled, either it will be stretched or it will become smaller or it will be flipped. Either this is the thing, that is the first thing, or it could be possible that after transformation it didn't stretch, the length remains same but it get rotated. So this is the thing. And it could be possible that the transformation T is doing a combination of both, that is it is doing stretching as well as rotation. So we will get something like this, right? So this is the first scenario. In this it is just scaling the vector. This is the second scenario. In this it is not scaling the vector, the length remains same but it just rotated it. And this one is the third scenario, which is combination of 1 and 2, that it scaled the vector as well as it rotated the vector as well. And this is not just true for V, this is true for the entire vector space. So the transformation, always remember guys, the transformation is applied on the entire input vector space. So if I say that I have this input space R2, this is input vector space R2, and I apply a transformation T, and I again get an output vector space R2, this is the input vector space and this is the output vector space, then this T is applied to the entire input vector space. So every vector get transformed. So for example, let us suppose if I am let us suppose my transformation is rotate the input vector space 45 degree anti-clockwise. Okay, so let us suppose this is my input vector space and this is my T, this is my transformation T. Okay, this is the input vector space, this is my input vector space, and this is transformation T. So which is saying rotate everything by 45 degree. So my output vector space will become something like this. You see everything is rotated by 45 degree, right? So always remember that transformation is applied to the entire input vector space. So in this case, here is my I hat and here is my j hat. So this also got transformed, and this is my new I hat and this is my new j hat. All right, we will dive into further details in the visual aspect of linear transformation. Okay, so if you see these two properties, right, we can combine them to get a single property for linear transformation as well, which is linear transformation LT is like T, linear transformation T of a linear combination of two vectors V and W should be equal to this. Okay, so this is linear transformation in one equation. So this is nothing but the combined form of the above two equations. Okay, either you can mention them individually or you can have a combined equation. So this is nothing but I just combine the above two equation, that vector addition and scalar multiplication. So this is the combined form of vector addition and scalar multiplication, right? Hi, here I am doing vector addition and scalar multiplication. So this is linear transformation. And always remember that the origin in the vector space, always remember that in linear transformation the origin never changes, the origin remains the same. Because see what I said, that we are doing just two things, a combination of two things, either scaling or rotation, right? So and this rotation about the origin, this is also important, about origin, right? So if I take the vector v equal to 0, the 0 vector, right? So if I scale the 0 vector, I get 0 vector only. No matter which number I multiply 0 vector, I will always get 0 vector. And if I am rotating 0 vector about origin, about itself, then I will end up in the 0 vector only. So always remember that T of v is always 0 if v is 0. That is, the linear transformation of the 0 vector, the origin is always going to be origin. So this is a very important property. I will mention the three properties of linear transformation later on. One of them is this, that origin doesn't change. So if the vector itself is 0 vector, then the linear transformation of that vector is always going to be 0 vector itself. Okay, the next important point is a linear transformation, LT is highly restricted. Highly restricted. What I mean by highly restricted? Okay, so let us suppose first answer this question. Let us suppose there is a linear transformation T. What it does, it just simply adds a vector uh, u naught to every vector, in the input vector space. This is the linear, this is transformation. I'm not saying it is a linear transformation or not, but this is a transformation. See, anything which do a change is a transformation, so this is a valid transformation. All right, this is a valid transformation. So it simply adds vector v0 to every vector in the input vector space. Now question is T linear transformation or not? This is the question. Is T linear transformation or not? So what we will do, we will check the property first. Okay, so the first property is vector addition. It says that if there are two vectors v and w, so for any two vector v and w in the input vector space, the transformation of the addition of these two vectors should be this. This is the property for linear transformation. This is one of the property. It need to satisfy both the property, but we will first check this. All right, so first of all, what is transformation of v? What I said, it just simply adds a vector to every vector. So transformation of v is nothing but v plus u naught. Similarly, transformation of w is nothing but w plus u naught, right? So what is the addition of these two? This is v plus u naught. I will simply add these vector, that's all, which is nothing but v plus w plus 2 times u naught. Okay, this is the left hand side. Now I will check the this is the right hand side. Now I will check the left hand side. This one, this is the right hand side. Now I will check the left hand side. Now what is the transformation of v plus w? Again I said, all you have to do is just take the vector. In this case, the vector itself is the addition of two vectors v and w, and simply add u naught, because the transformation T simply adds vector u naught, and v plus w is also a vector. So this is nothing but v plus w plus u naught, and we can say that LHS is not equal to RHS. So the property is not satisfied. So therefore T is not linear transformation, right? T is not linear transformation. But can we this is the one way of doing it mathematically, but it's you can see it's tedious, right? Can we answer this question visually using these transformation, the visual aspect? Yes, we can. How? See, when here I am saying that T adds a vector u naught. So when you are adding a vector u naught, then it's you are adding that vector to the entire input vector space. It's kind of a shift, right? And as I already told you that this is not a linear transformation. We can either only scale or rotate, right? In linear transformation, only two things are allowed: scaling, rotation, or a combination of scaling and rotation. So we don't even need to do all this. It's very simple to understand, okay, this is not a linear transformation. But yeah, for proof point of view, we can always follow this. We need to satisfy those two property to make sure that it is a linear transformation or not. Okay, so now the next thing, okay, now we will take another transformation. Now this is another transformation. This is a rotation transformation. Rotation by let us say 45 degree about origin. So is it a linear transformation? Yes, it is. It is like this. I already told you that by definition, kind of thing, that if you are just scaling or rotating or doing a combination of both, then it's a linear transformation. And we have already seen this in the above diagram as well, right? Here, see, this is nothing but the same thing. The T here is rotating 45-degree anti-clockwise. So here, if see, think this as a sheet of paper. This will be easier for you to visualize. Think the input vector space as a sheet of paper, which is a 2D xy plane. And now let us suppose you press the center of that sheet with your pen or pencil or whatever, and now you just rotate that sheet about that axis, about your pen. You are just rotating the sheet 45-degree anti-clockwise. You will end up here, right? So you will see everything on the sheet gets rotated by 45-degree anti-clockwise with respect to the origin, with respect to your pen which is holding the sheet from the middle, right? So this is just pure rotation, and this rotation transformation are always rotational transformation are always linear transformation. Okay, so here your input vector space, or also the domain is R2, the xy plane. In our example, is the sheet of paper, and the output vector space, the range, is also R2, the xy plane, the sheet. It doesn't change, right? So this is also a linear transformation. Okay, now this rule of linearity which I explained you, this rule, this is a generic thing. It can be extended to more than 2 vectors, 3 vector, n number of vectors. All right, so how it generalizes is something like that, something like this. For example, you have any vector u, which is nothing but a linear combination of n vectors, c1 v1, c2 v2, up to cn vn. So we have these n vectors, and u is nothing but a linear combination of these n vectors. Then the transformation of u, the linear transformation, T is linear transformation. Then the linear transformation of u is nothing but this. All right. So we see that this linearity property extends to any number of vectors, not constrained to 2 vectors or 3 vectors. This extends to any number of vectors, n vectors, right? So this is generic linearity property. Okay. Now we will dive. See, in the beginning I told you that this consider T as a black box, right? Now I will dive into detail, like what T is doing, what is this black box all about. Okay, so let us suppose we'll give it a new heading. So this is visual interpretation. All right. So let us suppose in the I am talking about the input vector space. This is the input space, and we have a line from vector v to w in the input space. So let us suppose this is the here we have v. This is the input vector space, and here is w. This is the output vector space. And when I am drawing this this thing dot, this basically is the tip. So for example, this is our vector space, right? So then these two are nothing but the tip of the vector. So v, the tail of v is at origin only. This is the tip. Okay, and let us suppose the midpoint of these two vectors u and w is u. All right. and then we apply a linear transformation T. So this is our input vector space, input vector space, and we apply a linear transformation T, and then we have this output vector space. Alright, this is linear transformation, and let us suppose we get this vector, the TV, the linear transformed vector TV somewhere here. Let us suppose we get W somewhere here, and okay, wait, let us suppose it get stretched. Let us suppose it got stretched a lot, and we get somewhere here. All right, and then this is the midpoint. This is vector U. So there is a very important point that linearity tells us every point on the input line. This is the input line, right? And this is the output line, joining the vectors TV and TW. So every point on the input line goes on to the output line. Okay, so this T is mapped to TV. All right, this T is mapped to TV. Okay, this W is mapped to TW. This U is mapped to TU. So this is the linearity. This is the linearity property. It says that every point on the input line goes to the output line, and not just that, equally spaced point go to the equally spaced point as well. So for example, in this case, the middle point U is nothing but the midpoint of V and W, right? And this thing, the midpoint of TV and TW is this, right? So the linearity, it just not say that every point on the input line goes onto the output line, but it also adds one more thing which is even more important. It says that equally spaced point goes to equally spaced points. So equally spaced point in the input space goes to equally spaced point in the output vector space. So if you see here, U is nothing but the midpoint of V and W, and the midpoint of TV and TW is this, and this is nothing but TU. So you see that in input vector space, U is the midpoint of V and W. In output vector space also, TU is the midpoint of TV and TW. Okay, so there are two important points mentioned here. Okay, the first point is every point on the input line. In this case, I am saying it line because this is the 1D representation, but it's not about just line, it's about the entire input vector space. It could be 2D, it could be 3D, 4D, anything. Okay, so but now because we are considering line here, so every point on the input line goes on to the output line. All right, and the second point, this is even more important, is that equally spaced points go to equally spaced points in output line, or here in input line. Okay, so these are two very important properties of linear transformation. Visual property. I already gave you two important just give me a minute. I already gave you two important things here, right? Where it is, yeah. The mathematical view of linear transformation, the two important things, that either it will scale the vector or it will rotate the vector. These are the only two things, or a combination of that, but at the core, these are the only two things which is going to happen. And in the visual world, in graphics, we have also two conditions. These are the two conditions. Either the first thing is that every point in the input line goes onto the output line, and second is equally spaced points in the input line goes to equally spaced point in the output line. So this equal spacing is also very important. Okay, now for more clarity, let's consider here I consider a line, right? The 1D representation. Let's go to 2D representation. Let's go to how the things changes in 2D world. So here I will be considering n square. Okay, so let us suppose this is the vector v1. This is input vector space. This is the vector v2. This is the vector v3, and this is the vector v4. And these are the tips of the vectors. Okay, the tail is always at the origin. So in this case, this vector v, this is the tip. This is something like this. Okay, so this is the tip of the vector. The tail is always at the origin, but because if I draw vector all the vector, then it will, the diagram become complicated. So I'm just representing them using their tips. Okay, again this is the input vector space. All right, and we have these joining these line, we have these midpoints. Okay, these midpoints. All right, so then we apply the linear transformation LT, and we have the output vector space. Now in the output vector space, again the two properties will remain same, that every point on the input line goes onto the output line. Equally spaced points in input line goes to equally spaced of point in the output line. So let us suppose this square expands, so now it becomes bigger. Let us suppose this one, and all right, and it also it's also kind of rotates, shifts, something like this. This is tv2, this is t times v1, something like this. This becomes t times v3, this becomes t times v4. Okay, so their midpoints, the midpoint of each side also maps. So let us suppose here we take the center, the centroid of this figure. All right, and the centroid is let us suppose the centroid is VC. So in this case the centroid VC is nothing but V1 plus V2 plus V3 plus V4 divided by 4, right? Similarly here as well, what is the centroid of these transformed vectors? The centroid is nothing but TV1, basically the average of all these vectors, these transformed vectors, right? And this is nothing but TVC. So not just these points get transformed, V1 transformed to TV1, V2 transformed to TV2, but because this is a linear transformation, it preserves the spacing as well. So it preserves the spacing of this vector, this VC from V1. Here it preserves the spacing from TVC to T1 as well. So everything get transformed. Okay, so the mapping, the spacing, equally spaced points stay equally spaced. So that is an important term which we like. If I summarize this, that equally spaced points stay equally spaced. All right, so if you see before, this is VC, right? This is VC, the centroid. Before transformation, the spacing between VC and V1, this spacing is same as the spacing between VC and V2. Okay, because this is a square, right? The same will happen here as well, because before transformation these two spacing, the space between vc and v1 is same as the distance between vc and v1 is same as distance between vc and v2. So even after transformation, this should be preserved. The distance between tvc and t1 should be same as distance between tvc and tv2. This needs to be preserved. Okay, so this is what it is mentioning, that equally spaced points stays equally spaced even after the linear transformation. Okay, so if I summarize, it says lines to lines. This is the first thing, that lines should be mapped to lines. Every point on the line goes to every point on the output line. Okay, lines to lines. Then the second thing is equal spacing to equal spacing. Alright, equal spacing in the input space is preserved in the output vector space. So equal spacing in the input vector space is equal to the equal spacing in the output vector space as well. And the third one, which I stated above as well, that for the zero vector, okay, if v is zero vector, then its transformation tv is also zero vector. And this I already stated here, because we are rotating about the origin. So origin is always preserved. See, here also it is mentioned. So you can see that everything whichever I explained in this mathematical aspect, the scaling, rotation about the origin, is mapped very beautifully to the visual aspect, that lines to lines, equal spacing to equal spacing, and one special case, that the zero vector, the origin always mapped to the origin, because we are just scaling or rotating. And if you scale or rotate the zero vector, you end up in zero vector only. All right, so these are the three things: lines to lines, equal spacing to equal spacing, and v2 tv0. So apart from this, yeah, this I can also say in simple terms, that origin doesn't change in linear transformation. And lines to lines, basically lines remains lines after linear transformation, right? Equal spacing to equal spacing. So for example, this one, if this is your input vector space r2, and this is your input vector space in the grid line format. Okay, so no matter what transformation you apply, no matter what linear transformation you apply, let us suppose you are rotating it by 45 degree. So even after applying this 45-degree linear transformation, the spacing between the grid lines remain the same. Okay, the spacing between the grid lines remain the same. So equal spacing to equal spacing, basically we can say that grid lines remains equally spaced and parallel as well, because it's line to line, so it needs to be parallel. All right, okay, now the last thing. See, I always end for the last lecture, I am always ending with the basis for vector space, basis vectors, right? That's why basis vector is very important, like this is the core. And even in linear transformation, I need to end it with basis vector because it's so important. All right, so for example, we have this vector v. This is the input vector space. So we know that v is composed of two special vector, the unit vector I hat and the unit vector j hat, right? So v is nothing but some combination, uh, let us say vx I hat plus vy j hat, where I hat and j hat are standard basis vector for R2. Now you applied a linear transformation LT, and this becomes something like this. Maybe, yes, maybe something like this, right? And your I hat goes here, your j hat goes here, something like this. Your grid lines are now okay. So basically this linear transformation is 45-degree anti-clockwise rotation, AC rotation. Okay, so you just rotate it, you just rotated this vector 45-degree anti-clockwise, and the length remains the same because in rotation length doesn't change. Then there is an interesting property. This transformed V, that is TV, this linear transformation of V, TV, is in fact it is the same linear combination Vx and Vy. It is the same linear combination. Here also it is the linear combination Vx and Vy of I hat and j hat. So it is the same linear combination Vx and Vy, but not of I hat and j hat, but the transformed I hat and transformed j hat. Okay, so here V is a linear combination of I hat and j hat. Here also transformed V is the same linear combination. You see Vx and Vy doesn't change. Vx and Vy remains the same. So it is the same linear combination, but not of I hat j hat, but the transformed I hat and j hat. All right. So there is something called basis tells everything. So what I mean by that? So if you know the basis, suppose that we know the transformation for all the basis vectors, then we know what is the transformation of any vector. So for example, if I know what is t I hat and t j hat for in R2, then I know what is the transformation of any vector in this input vector space. All I need to know is these two values, ti hat and tj hat. That's all. Because if you see, if I know ti hat and j hat, if I know this and this, and you give me a vector, because you are giving me a vector, then I already know vx and vy. Then and I am saying that I also know ti hat and tj hat. So then I know the transformation of any vector. So to find what is the linear transformation of any vector, all I need to do is the what is the linear transformation of the basis. So if I generalize this, then if I say, if I know t of u, vector u, for all basis vector u1 u2 up to un basis vectors in Rn, then I know transformation for any vector v in Rn. So for example, if the input vector space is R cube, so to know how a linear transformation T transform any vector in the input vector space R cube, all I need to know is what is the transformation of I hat, what is the transformation of j hat, what is the transformation of k hat. That's all. Because let us suppose I have this vector v in R3, which is nothing but let us suppose 1 2 3, right? And how I can represent this is nothing but 1 times I hat plus 2 times j hat plus 3 times k hat, right? This is this one, this is this thing. Zero zero one. Okay, so if I need to find TV as I already told you, TV is nothing but the same linear combination, 1 plus 2 plus 3, but transformed I hat, transformed J hat, and transformed K hat. All right. So all I need to know is what is the transform I hat, transform J hat, transform K hat. If I know this, then I know transformation for any vector in that vector space. So that's why we say that all we need to know for a given transformation T, we just need to know the how it transform the basis set, the basis vectors. If we know that, then we know everything. All right. So this is why bases are very important, guys. Like bases, that's why we say bases, right? Base of the vector space. So we, if we know how the linear transformation T is transforming the basis vectors, then we know everything. Then it's done. We know everything after that. Okay, mostly done. Just one more thing, that you are going to tell me this. Suppose we have two linear transformation, T1 and T2. T1 and T2 are linear transformation, right? And we apply a product of these, that is T1 into T2, and we apply this thing to an input vector space. Then is it still linear or not? Pause and think. So it is linear, right? It is still linear. So for example, I have a vector V. I first apply T2. Then I will become then I will get T2V. Now because T2 is a linear transformation, so T2V is also a vector with its tail at the origin. That is fine. This is nothing but a vector. And after that, what I am doing, I am applying another linear transformation T1, and then because T2V is already a vector, so this is just a vector, nothing, right? T2V is just a vector. So this T1 T2V is also a linear transformation. So yes, T1 and T2 is also linear transformation. And not just that, any product, like if you take n number of linear transformation, T1, then apply T2, then T3, up to so on up to Tn, and all T1 to Tn are linear transformation, then this entire product is also linear transformation. So product of two linear transformation is still linear transformation. All right. Product of not just two, product of n linear transformation is also a linear transformation. All right. Okay. So this is the thing. Okay, sorry guys, this is not V, this is TV, transformed V. This is transformed I hat, and this is transformed J hat. All right, I can write this, transformed I hat. This is transformed J hat. Okay, so that's all. I think we covered everything for today's lecture. All right, so what we covered today, linear transformation, both mathematical part and the visual part. I explained this, what transformation is actually doing visually to the input vector space, right? The rotation, the scaling, it preserves that lines goes to lines, equal spacing, origin remains origin, all those things. Okay, so if you have any doubt, then comment below. If something is not clear, then comment below. I will clear your doubts. If required, I will explain it further in the upcoming video lectures. Okay, so if you find my videos helpful, then please subscribe my channel, like my videos, and share with other GATE aspirants or ML engineer, data scientist. All right, because it is helpful for everyone. Okay, see you then next time. Bye.